Okay, we have one more video. This one will be more of a skim than anything else. Now, you may be like, what? We already went through IRR? Isn't that enough for today? No. We're going to go through one more thing, which is the theory of NMR. This is maybe less important that you memorize this, but it is good to give you some background of this. So, I don't have the slides posted online. The notes are maybe not going to fit as closely to what we're going to talk about, but we will be going through the theory of how NMR is technically supposed to work. So, once again, this was for my organic spectroscopy course. So, fundamental theory. So the idea here is that any discussion about NMR needs to talk about the idea of a quantum spin number, which has to do with the spin orientation. The idea of that the atom, we all know that the electrons spin. Well, the atoms also spin. Everything is spinning. And for every given atom, there is a 2i plus 1 number of degenerate spin orientations. The common electron, we say it's 1/2. So 1/2 times 2 is 1, plus 1, there's 2 spin orientations. Spin up, spin down, which is our counterclockwise or clockwise spinning. They're each producing its own small magnetic moment, based on what we call the right hand rule, where if you hold your right hand, curl your fingers in, either clockwise or counterclockwise, the thumb points the direction of the magnetic moment. So counterclockwise spin has an upwards magnetic moment, clockwise spin, a downwards magnetic moment. Well, the nucleus could spin based on the total number of nucleons, which is its protons and neutrons. And here's the weird thing. If a molecule has an even number of protons, so atomic number even, and an even number of nucleons, so even mass, even proton count, it has an I of 0, which means 0 times 2 is 0, plus 1, it has 1 spin orientation. Thus, it has no magnetic moment. Now, if a molecule has an even atomic mass but an odd atomic number, it has a positive integer of I. Now, this I could be 1, could be 3, could be 5, could be 4, could be 6, could be 7, could be any kind of positive integer. If it has an odd atomic mass at all, it will have a fractional I, say like 1/2. So 3/2, 5/2, etc. But so either way, these are going to result in multiple degenerate spin orientations that are possible. Now, these, for example, hydrogen with its odd mass, odd atomic number, has a I of 1/2, meaning there's 2 possible spin states. The majority of our measured nuclei, carbon 13, fluorine 19, phosphorus 31, will have an I of 1/2, so they'll only have 2 possible spin states. But it is possible to measure magnetic moments of other unusual spin states. But okay, so the degenerate. Degenerate means they have the same energy. You can't tell spin up or spin down. However, when we apply a strong magnetic field, you're going to separate these spin states into 2 different energy states. One is going to be a lower energy state where it's aligned with the field. So it's like you're running with wind. If you're running against the wind, you have to use more energy to move forward. If you're running with the wind, it's less energy to move forward. So we separate the 2 degenerate spin states into a lower energy spin state and a higher energy spin state. So the atomic spin, and there's various different things, but essentially with increasing magnetic field, you see a greater separation of these spin states. Now, so jumping back, we have the energy based on that. Then there's let's see, just okay, more frequency ratio. Okay, so there's a frequency related to this that can be where we can excite them up from one spin state to the other, where it has to do with one, the gyromagnetic ratio of the nucleus, times B sub 0, which is the magnetic field strength, over 2 pi, which is of course a constant. So the energy it takes to jump from one spin state to another has to do with something that's dealing with the atom, and something that's dealing with the magnet. Stronger magnet, it's going to take more frequency. This energy difference will then relate in a Boltzmann distribution model of nuclei, so that even though we have lower energy and higher energy, that doesn't mean all atoms are in the low energy spin state. Just that there is a majority of the atoms in the lower energy spin state, and that ratio of low to high has to do with the exponential of the change in energy over Boltzmann's constant times the temperature. So largely speaking, as the energy gap increases, more nuclei will be in the lower energy state. But at higher temperatures, they can be equally filled. Basically, not all atoms will have the same energy. Not all atoms will have the same energy, so if some of them have enough energy, they can adopt the high energy spin state. Now, if you give all of them more energy, then it's going to be equal distribution. So the only two variables we can control to get a wider distribution is a stronger magnet and change the temperature. But however, these are often instrument dependent and thus hard to change. And so largely what we will measure in these experiments is what's called the Larmor frequency in megahertz, which is the energy it takes to induce a spin flip in the nucleus. So we're going to excite all the atoms into the high energy state and let it decay back down to its normal distribution model. So every NMR contains one, a stable magnetic field of strength B0, a radio frequency transmitter that's we use to excite all the atoms using to spin flip, and a sensitive RF receiver, the detector, and a computer that's going to control these pulses, and finally a printer that's something that's going to deliver the spectrum so we can read it. Now, the early spectrometers used a continuous wave method, which is just like the simple monochromator in the IR, where it simply swept through the RF range, exciting one atom at a time, and recording the data based on the absorption of energy as a function of the frequency. But this process, as you can imagine, is very slow, because you're shooting through all the radio waves one by one by one. You have to let decay, and they don't decay instantly, so you have to take a lot of time. Now, our current spectrometers will use a pulsed radio frequency that excites all the atoms simultaneously. Now, as the samples will relax down to the ground state, they will release energy that produce a complex sine wave exponential decay called a free induction decay. It's going to look essentially like these. Now, this can be analyzed once again through Fourier transform to become a readable spectrum as a function of frequency. So we're going to have multiple different excitations and let them all decay, and excitations and let them all decay, and get a nice, really complicated pattern, but the computer does all this analysis and turns this into something we can really analyze. Well, this method will allow rapid analysis of sub-milligram quantities and makes it possible to even analyze carbon-13 in its natural abundance. So the idea, as we said, carbon-12 would be NMR invisible. It has only one degenerate frequency. So carbon-13 is necessary. Carbon-13 is only about 1% abundance. So we're looking at millions and millions of atoms. Only 1% of those millions of atoms would have a carbon-13. Then what's the chance of that carbon-13 being in the correct spot? So if you have a 20 carbon atom, you have a 1% chance that the carbon in carbon 1 has a C13, a 1% chance of carbon 2, and so on and so forth. And you need to find enough of carbon 1s and C13s and enough of carbon 2 and C13s to see all the carbons. If you can't analyze all the carbons, it's really hard to take a really small quantity and turn it into readable data. Now, here's some really complicated bullshit, but essentially what it comes down to is that we have a randomized spin, but under the magnetic field, it's going to orientate itself in the upward spin and the downward spin. So it's precessing in a random phase around the z-axis, but none in the xy plane. We're going to apply the Lawnmower frequency. We're going to spin flip them all. The idea is to tip these guys out of the z into the xy plane and want some, like a top, reorientate itself. Like it's spinning so fast it like picks itself back up. And so we're measuring as it goes. So we knocked it here, and so as it tries to reorientate itself, it's going to wobble itself back to its original state. And as that, how it's wobbling, we're going to be able to pick up the radio frequency created by these spins. So, and the idea is we're going to essentially hit it, knock it on its side, and then so it's going to start spinning around as it comes back to here to its normal frequency. We're going to analyze that. Now there's going to be some sort of time period between which where we're going to have to let it. We're going to have to let them go back. Sorry. We're going to have to let them essentially reset themselves before we can acquire again. So atoms are going to be in different point in the precession, so there's lots of things we have to deal with. But okay. But since the oscillating field would create a pulse V1 out of the Lawnmower frequencies, some atoms will have frequencies lower or higher than their V1, and thus they'll be moving faster or slower. And basically you'll get like the positive, you'll get this, what's getting a sine wave based on where they're actually at from this free induction decay. Don't have to worry so much about this, but just know that we're going to analyze this multiple times, and we'll get a high signal-to-noise ratio based on the square root of n once again. Now, one of the things that we have to worry about is relaxation period. How long it takes the atoms to reorientate themselves. So we've hyper-excited everything into the high spin state, and we have to let it reorientate itself by relaxing back down. We have some spin lattice relaxation and spin-spin relaxation. So some of this is due to the spin lattice is how it natural vibration and rotations through the structure lattice comes down and spin. And generally speaking, it's about 63% of we calculate as a time for about 63% to reorient itself. But this is a function of the gyromagnetic ratio. So, let's say molecules have a long. One thing we have to worry about, for example, is if they have a long relaxation period, not all the signal will be accounted for in a given atom, as some of the molecules are still in the process of relaxation before the second pulse goes to analyze the second set. So there's a lot of fancy NMR techniques you can do, like changing the relaxation times or changing how long it takes between pulses. It takes some programming skills, but it's possible to play around with this to get more signal. So some signals will not get will not be able to measure all the signal because they have a longer relaxation time. But then T2 is the rate at which nuclei relax out of the XY plane, typically through energy transference between nuclei of identical rotational energy. See, it's basically dephasing. See, but these things will typically result in broader peaks. Let's see, This is stuff we don't really need to worry about. But so relaxation effects. Largely speaking, the mechanism of T1 is dependent on the adjacent nuclei and the relative magnetic moment and the separation based on distance. Let's see. Relaxation first order, so we get a Lorentzian curve. So usually it's not just a single peak, it's actually a width of the peak. Based on where important properties, the curve, its full width is 1/2 of V of 1/2 in the hertz, where it's inversely proportional to the T2 relaxation in seconds. Blah, blah, blah. We see this means longer relaxation time results in sharper peaks. But shorter relaxation, especially from nuclei adjacent to nuclei with large magnetic moments, can be particularly broad. So, large magnetic moments can make broad peaks. But if we give things more time to relax, we're going to have sharper peaks overall. But so some of those things are going to be out of our control. Okay, relaxation time will also affect intensities. Because the area under a spectrum, under this curve, correlates with the number of nuclei involved, assuming all nuclei are allowed to fully relax. So if all nuclei are allowed to relax, we're going to see a direct correlation, an integration over the curve is going to measure the area under the curve of one hydrogen is going to be equivalent to another hydrogen. But if a hydrogen isn't allowed to relax all the way, you're not going to get a tall enough peak. Where this is going to deal mostly with is carbon-13, as we'll see later. Carbon-13 have a particularly long relaxation time. So not all nuclei may relax before the next pulse. What this is going to mean is that because carbon-13 will often couple with hydrogen nuclei, if there is a hydrogen bound to a carbon, we have a much faster relaxation time. And what essentially happens is primary, secondary, and tertiary carbons have equivalent relaxation times, but quaternary carbons with no hydrogens attached, relax so slowly that we lose a lot of the signal intensity. So quaternary carbons are often really small or even hard to see at all because they take too long to relax. So when we look at carbon-13 NMR in a little bit, they may be unusually small because of that. But so it's one of the reasons why we cannot directly integrate a C13 NMR, because if you don't get every single quaternary carbon of the correct intensity, even if there's one quaternary carbon and one tertiary carbon, they're not going to have the same intensities, and so you can't directly correlate them. Now, another thing we have to worry about is magnetic shielding. Now, this is what's really important. Magnetic shielding is basically, if there was not magnetic shielding, all protons, all hydrogens would excite at the same Larmor frequency. All carbons would excite at the same Larmor frequency. However, as nuclei have magnetic moment is placed in a magnetic field, it will create new magnetic lines of flux in opposition to the original magnetic field. So there is some shielding due to the nearby nuclei. There's some sort of shielding. Now, this shielding is going to change their Larmor frequency. So, depending on what things are bound to, depends on where these guys excite at. And so, this is going to result in different chemical shifts. So, one hydrogen is not equivalent to another hydrogen unless they are symmetric. So, we're going to measure things as chemical shift. It's typically plotted in units of hertz, which has to do with radio frequency, but we often convert that into parts per million, which will decrease in number from left to right. So left is the high ppm, and right is the low ppm. This convention is left over from when the frequency was left constant and the magnetic field was swept, so that the Gauss would have increased from left to right. But as a result, we sometimes call low frequency shifts upfield on high frequency shifts downfield. So shifting to the left is downfield and shifting to the right is upfield, even though we have low numbers on the right. When referring to electronic character, the shift low frequency nuclei are shielded and high frequency nuclei are deshielded. So, but generally speaking, the frequency hertz is converted to conventional delta values of ppm through the following method. We're going to take the shift of our sample versus a shift of a standard, all divided by the frequency of our magnet. So we're going to compare these guys to a standard and then measure that. Now, our standard we often use is called tetramethylsilane, TMS. Now, this has a very specific purpose in that TMS can be added. It's very non-reactive. Tetramethylsilane is just basically, imagine instead of a quaternary carbon surrounded with 4 methyls, it's a quaternary silicon surrounded with 4 methyls. Now, what we know about silicon is particularly electropositive, less negative than carbon. So carbon suddenly becomes the electronegative one. And so what happens when you have a positive electropositive carbon, electrophile in the center, and nucleophiles on the outside? The electrophile is going to start pulling electron density, but the carbons are going to start pulling electron density out of that silicon. So the carbons are going to get more electron density than what they would expect, and they become shielded. So they're pulling electron density from that silicon to the carbons, and so they go upfield, much further upfield than most carbons will usually go. The same thing is going to happen to that hydrogen. So since those hydrogens are going to be attached to that carbon, which are attached to the silicon, there's going to be more electron density around that carbon, which means there's going to be more electron density around those hydrogens. They are going to shift further upfield than most carbons and hydrogens will usually go. And we are going to artificially set that as 0 ppm. And from there, every shift that has less electron density is going to be in the positive range. So we're setting an artificial 0 that we can measure everything else off of. However, if you were to have, say, a metal bound to a carbon, metal might be even more positive than silicon, and thus result in negative shifts. So it's an artificial 0. There's no absolute 0. It's just a shift relative to our standard. Now, one other thing to consider is that why we use deuterated solvents. Why do we use deuterated solvents? The idea is that we are measuring all hydrogens and all C13s. If we have a solvent that is made up of normal hydrogens, the hydrogen of the solvent would be in so great abundance that our sample size would be incredibly small and overwhelmed by our solvent. However, by changing out a deuterated solvent, the amount of normal hydrogenated solvent, protonated solvent, is only 0.1%. So there will be some of the solvent that has not been deuterated, but it's usually such a low percent that we don't have to worry about it. So this will give us something to kind of lock onto, that we know where it's supposed to be, but the solvent will dissolve this and the deuterium will shift at different radio frequencies and thus will not really be seen. Yes, you could probably study deuterium, but we don't. So this avoids obscuring the sample, and it will also allow the spectrometer to create a deuterium lock, because it knows where you tell it, I'm using deuterated chloroform, and it knows where deuterated chloroform will be excited based on radio frequency, and so it knows kind of where it's studying. So this lock will help prevent magnetic field fluctuations and will help decrease signal to noise ratio. But so we will always have a little bit of solvent impurity in there. It can be used as an internal standard, much like TMS. And so we often use deuterated solvents like deuterated benzene, deuterated chloroform, deuterated acetone, deuterated water, deuterated DMF, deuterated DMSO, dimethyl silicon oxide. It all depends on how organic or how polar is your compound that you wish to study. But that is the theory. As I said, I kind of went over some of it fast. I kind of went over some of it poorly, because the basic idea is we need an odd mass, an odd odd atomic number, which is why we use protons and C13. We need, depending on the chemical environment, these guys will be excited by a different radio frequency into a high energy state and will eventually relax back down to a low energy state. And the degree of electron density and what is attached to it will control where the frequency calms down at. And we'll see the peak width and the peak area has to do with how much signal we have and how long we're going to allow it to relax. We have to use deuterated solvents to avoid overwhelming this with our sample with the solvent. And we have to use standards to help determine where the shifts are. There's no true zero, it's all artificial. But with that in mind, we're going to start looking at some proton NMR and how to actually interpret that come next week.